All right, it is 2 o'clock, so let's go ahead and get started. Our colloquium speaker today is Vereese. Vereese did grad school and undergrad at Cape Town in South Africa. She was an employee here for 2 years after that, at which point now she is working back at MeerKAT and is going to tell us about the MeerKAT Radio Telescope. So please join me in welcoming Vereese.
Thank you very much for that introduction. So as Dr. Butterfield said, that I will be talking to you guys today about the MeerKAT Radio Telescope, which is a newly constructed radio telescope in South Africa. So I'd like to start the presentation by just giving a quick overview. Firstly, I'll talk about why did the telescope get the name MeerKAT? And then I'll go on to where is MeerKAT located. We'll look at what constitutes the MeerKAT Radio Telescope, and then we'll look under the hood to see how MeerKAT actually processes the data from space. And then we'll look at some science with MeerKAT. So why MeerKAT? So originally the telescope was going to be called the Karoo Array Telescope, and that stands for CAT. But then it got extended, so originally there was only going to be 20, and then it got extended to 64, so then they called it MeerKAT, which translates, so in Afrikaans, Meer means more, so it translates into more cats. But at the same time, it's a very, very cute mammal called the MeerKAT that you can find around site and other places in South Africa as well. And you guys can try and pronounce that scientific names. I definitely can't, like suricata. Yeah. So where is the MeerKAT Radio Telescope? In short, it's in the middle of the Karoo Desert in South Africa, which is a place with stunning sunsets. So as you can see in this photo, it's spectacular sunsets. But also Google knows where MeerKAT is. And this is a map of the southern part of Africa. And this is an outline of South Africa. And this red marker is where the MeerKAT Radio Telescope is located. So the South African Radio Astronomy Observatory actually consists of multiple sites, of which MeerKAT is located there. And it's also located in a radio quiet zone, which has a radius of about 70 kilometers around the core of the MeerKAT Radio Telescope. And right here at the edge of the radio quiet zone lies a small town of Carnarvon, which we have as SKARAB offices. We also have offices in Cape Town. That is where I am based. This is also where the main MeerKAT control room is located. However, there is a small operations control room at site as well. Then up in Johannesburg, which is close to Pretoria, we have the Hartebeesthoek Radio Telescope, and that is the telescope that was built way back in the 60s by NASA, and it was used as a communication downlink station for the Apollo 11 mission. So the Hartebeesthoek Radio Telescope also now forms part of the South African Radio Astronomy Observatory, and there's offices in Johannesburg as well. So if we zoom in a little bit more, we can actually see what the site looks like, but you guys can see that this is an outdated satellite image because there's no dishes actually up there. However, you can see the locations of the individual MeerKAT dishes. So over here is the core of the MeerKAT telescope. It's an area with a diameter of 1 kilometer. And there's 64 antennas, and 75% of the MeerKAT dishes are located within this 1 kilometer diameter. So that's 48 of the dishes. Also in this picture, you can see the CAT-7 precursor radio telescope. Well, you can see the location to the of the Cat7 radio telescope, which is the precursor to the MeerKAT radio telescope. From Cat7, there's a road that goes up to this circular area, which you guys can see, and that's the location of the Hera radio telescope. This is a road that comes in from Karoo, and this is the Losberg site facilities. It was named after the Losberg, so this mountain is called Losberg. And we'll look at the Losberg facilities a bit later during the talk. A baseline is defined as the distance between two of the dishes, and MeerKAT has a maximum baseline of 8 kilometers. So that means that the furthest distance between any 2 points of a MeerKAT, between any 2 MeerKAT dishes is 8 kilometers. So just as a side note, and in case you guys were wondering what these other telescopes that I've been mentioning looks like, this is the Cat7 precursor to MeerKAT. And down here we have the Hartebeest Hoek radio telescope, which is situated, so this is the telescope that was used during the Apollo mission. This smaller telescope over here is actually the precursor to the Cat7, which is again the precursor to MeerKAT, which you can see here in the distance of the hydrogen epoch of reionization, the Hera array. And the reason why I really want to show you guys this, as I'm sure you know, is that the Hera prototype was built out here in Green Bank. So what is MeerKAT? MeerKAT is an interferometer, and that means that it is individual radio telescopes that gets combined in order to form a larger dish. MeerKAT is also a Gregorian offset antenna. So here you can see the main dish. The main dish has a diameter of 13.5 meters. It has a pedestal, it has a sub-reflector, and it has a feed indexer. So the astronomical sources comes from space, goes to the main reflector, gets reflected to the sub-reflector, and then to the feed. The slew rate in the azimuth direction for MeerKAT is 2 degrees per second, and it can turn, so it's like 0 is in north, and then it can go to negative 180 and then to positive 275 degrees. It can, the slew rate in elevation is 1 degree per second, and it can go all the way down to 15 degrees and then all the way up to 88 degrees. Each antenna is about 19.5 meters tall and weighs 42 tons. So the rotating turret has 4 receiver slots. L-band has been fully installed and is operational. UHF band, all the receivers have been fitted, and 58 of the digitisers has been shipped to site, and like the installation process is ongoing, and the S-band receiver is also, deployment of the S-band receiver is also underway. We are also exploring X-band in the future, but it's not in the budget for this financial year. So all of the radio frequency, all of the RF signals are sampled at the feed. And this is a zoom in of what the feed indexer looks over here. So these are the receivers. The job of the receiver is to take is to collect the radio signal and convert it into an electrical signal, which is an analog signal, and that analog signal gets sent over a coaxial cable to the digitizer, which is the unit that is responsible for converting that RF signal into a digital signal. The pointing accuracy of the MeerKAT is 25 arc seconds, and the base pointing accuracy is 5 arc seconds. The total collecting area of MeerKAT, so let's do that calculation. So it's 13.5 meters for one telescope. That gives you 143 meters for area for one telescope, and then that times 64 is approximately 9,164 square meters for the entire array. Construction of MeerKAT began in March 2014, and the telescope was inaugurated in July 2018. Each of the dishes were assembled on site, so they couldn't be shipped as they are. There's a shape that I will show you guys a bit later. Each dish consists of 40 aluminium plates, and they're fitted onto a steel framework. Once the dishes has been assembled, they get transported on this abnormally large truck to where the MeerKAT is located, and then it had to be hoisted using a crane. So this is the Losberg site facilities. Over here you can see the shed in which the panels were assembled. I actually got to see the very last dish being assembled. I was on site during that time. It was very exciting to see the last MeerKAT dish being assembled. This is the diesel tanks on site, and this is staff facility, housing containers. And this over here is the Karoo array processing building, which is the Faraday cage that houses all the electronics on site. During the inauguration, there was a small model of what the interior of the KAP shielding room looks like. So you can see the honeycomb structure over here. This building is also built into the ground, so it's approximately 1 story level into the ground. And you can't see it in this picture, but there's a heap of ground that also provides another 20 dB of shielding for the telescope. So now we can go to the next section, and we can look under the hood of how MeerKAT actually processes the data. And in this section, we'll give a system overview. We will look at the L and the UHF band receivers. We will look at the time and frequency reference system, and we will look at the digitizer units, and then we will look at the correlator beamformer. So this block diagram gives an architectural overview of the telescope. You've got 64 inputs, and you can select. So this is on one antenna. So you've got the receivers, and you've got the digitizers, and you can select either UHF, L, or S-band. This goes, after it's being digitized, it gets converted into an optical signal, also in the digitizer units, and that goes to the receptor switch. The receptor switch then goes to the fiber patch, and this is where the signal gets transported to the Karoo array processing building via fiber, which is buried 1 meter under the ground for temperature stability. Once the signals get to the Karoo array processing building, all the data gets plugged into a 40 gigabit Ethernet switch. An F engine is the fast Fourier transform. This is the unit that channelizes the data into different frequency components. The X/B engine, like an X engine is the correlator, and the B is the beamformer. There's also user-supplied equipment, and user-supplied equipment can easily integrate with MeerKAT because we make use of multicasting. The following data streams are also available for the user-supplied equipment to subscribe to. So if you've got use equipment, it can subscribe to the raw data coming from the digitizers. It can also subscribe to the F, it doesn't have to subscribe to the digitizer. It can decide to take the data from the F engine, or if it wants to use the data from the X or the B engine, it can subscribe to that data. The data products from each of these processing nodes are packetized as speed streams. Speed is the streaming protocol for exchanging astronomical data. And now that we've looked at an overview of the system, we can go have a little better look at the different subsystems. So this is what the L-band, this is an L-band receiver, and this is what it looks like in the lab. It's got its protective dome removed here. And this is the front view, and that is the back view. These circles are called concentric choke rings, and they form part of the waveguide of the receiver. If you add or remove some of these, you actually change the beam pattern of it. And the dipoles, which you guys can see in these pictures, they actually sit right behind the feed. So this is the part that picks up the signal from space. MeerKAT has been optimized for having a low side lobe level. So when you look at the radiation pattern of any antenna, it will have side lobes. So you will have your main lobe, and then you've got your side lobes. And the relative difference between the main lobe and the second main lobe of the L-band receivers is 26 dB. The bandwidth of the UHF band receiver is 580 to 1010 megahertz. And for the L-band receiver, it's 900 to 1670 megahertz. Did I get that right? So I said UHF band first, right? Okay, great. Okay, here is a block diagram of the L-band receiver. So you can see the dipoles and the ONT, and you've got vertical polarization going to one low noise amplifier, and you've got horizontal polarization going to another low noise amplifier. The receivers make use of two-stage cooling. This part is kept at 20 Kelvin, and the second stage is like room temperature. The calibration source sits in the second stage, and that is a noise diode, and the noise diode gets controlled by the digitizer. So this graph shows the receiver temperatures, noise temperatures. So this graph is like measures from the lab. The system noise temperatures when the antenna is fitted onto the telescope is 22.5. So for each polarization and their combined average, the system noise temperature has been measured. So next, I would like to tell you guys a little bit more about the time and frequency reference subsystem. So this is the subsystem that provides timing to the telescope, and it also provides the pulse per second for the telescope. So we have two hydrogen masers provided by T4Science, and the time and frequency reference group consists of the Karoo array timing system, the sample clock generator, and the pulse per second transmitter. So there's also a timing master controller, and the timing master controller is in charge of calculating KTT, which is the Karoo array telescope timing. Karoo telescope time. The CATS system is the system that's responsible for measuring the round-trip delay to the antennas and to accurately timestamp the data. So there is a signal that gets sent from the KAPB building to the antenna, and then it gets reflected back. And that offset is measured and then used to accurately timestamp the data products. The hardware that gets used in the time and frequency reference subsystem is the two hydrogen masers. Then we have Septon Trio GNSS receivers connected to the masers. And we also have two rubidium standard GPS clocks. And all of these clocks get combined in order to form KTT. So next up, I've got the UHF and L-band digitizer. So this specific picture is of a UHF band digitizer. And I would just like to remind you guys that at this point, the signal coming in is still an RF signal. So over here, you guys can see the SMA connectors, and this is the connector for the optic fiber. Because the digitizer units sit right up at the telescope, we really needed to make sure that it doesn't emit any RFI. So all the electronics is inside an RFI shielded box. And in turn, these RFI shielded box is in an RFI shielded box. So need to get this right. So over here is the RFCU, that is the radio frequency conditioning units. That's the units that contains the anti-aliasing filters, and these filters are important because MeerKAT makes use of bandpass sampling. So the anti-aliasing filters need to have nice and sharp edges so that none other interference gets sampled down into baseband. So that's the use of the anti-aliasing filters. So we've got an RFCU for the H polarization and V polarization. Then we have two sampler units. So those are where the ADCs are actually located. And you can see the fiber units coming out here to what is called the D engine. And this is the unit that packetizes the data, which takes the optics data and packetizes it into the speed format. And then at this point, it's 10 gigabits per second Ethernet times 4 that goes into the antenna pedestal. And then from the antenna pedestal, it's a 40 gigabit Ethernet link that goes to the Karoo array processing building. So data rates, it's 10 bits times 2 polarization, and we sample at 1,712 megasamples per second. So that produces 34,240 gigabits per second per antenna. So that's the digitizers. Let me just make sure that I said everything that I wanted to. For the electronics group, the digitizer unit is fitted with a Kintex 7 FPGA. So next up, I just want to give a quick overview of our correlator beamformer architecture. This block diagram shows the interface between the digitizers and the processing nodes. So for MeerKAT, the processing nodes are SKARAB boards, and SKARAB boards are FPGA boards. And recall from the previous slide, I said that there is 34,420 gigabits per second from each antenna. So times that times 64, it produces 2.2 terabits per second. And all of that data gets plugged into multicasting switches. So there's multiple switches which this data plugs into. So the processing nodes, they can are SKARABs, and a SKARAB can be configured to be either an F engine or an X engine or a B engine, and it can do this because of the field programmable gate array FPGA technology. SKARAB is fitted with a Virtex 7 FPGA, and this is a picture of the SKARAB boards. And yeah, it's like, so the FPGA is underneath the fan. So for the F engine, there are 3 frequency granularizations that MeerKAT currently implements. There is the 1K mode, the 4K mode, and then the 32K mode. And MeerKAT can also form subarrays. So this means that you can split the 64 antennas into different subarrays. You can have, for example, one 16 antenna array doing holography, and another 16 array doing software tests, and the other 32 being used in 32K mode. So over here, this is a picture of what the Karoo array processing building looks like on the inside, and you can see the SKARAB racks over here. In total, there are 288 SKARAB boards. We have 54 Mellanox switches. Each of the Mellanox switch has 12 40 gigabit Ethernet ports. So next up, science with MeerKAT. So MeerKAT has many large survey projects, and I'll only be covering a few. We also have telescope open time, and we've received about 25 proposals this far. And in this section, I will be talking about the UV coverage for MeerKAT. I will talk about some science projects for MeerKAT. I'll talk about MeerTime, and I'll give an overview of a recent discovery that was made with MeerKAT. I'm just going to grab a bit of water. Any questions so far? Are we doing questions afterwards? Yes, Paul.
Are we doing questions afterwards?
How would you guys want to do it? Afterwards?
That's your question.
Okay. Yeah, maybe I should finish up the science and then we do questions afterwards. How does that sound?
Very good.
Okay. So an interferometer like MeerKAT has a synthetic aperture, and this synthetic aperture is called UV coverage, so UV. The UV coverage is dependent on the number of antennas in the array, the configuration of the array, the frequency that you're observing at, the declination of the source, and the length of your observations. So remember, like at the beginning of the talk, I talked about baselines and how a baseline is the distance between any two telescopes, well, any two antennas in the telescope. So for each baseline, at a specific point in time, you get one sample on the UV coverage plane. And MeerKAT had the calculation for the amount of baselines is n times n-1 divided by 2. So for MeerKAT, that is 2016 baselines. So that is 2016 points on the UV plane, and then as you observe for longer, it creates these tracks. So this is for an observation of 8 hours long with a source declination of negative 30 degrees. So science with MeerKAT. As I mentioned, we have a lot of large survey projects, of which ThunderCat, TRAPPIM, Breakthrough Listen is a few. MeerLicht is not MeerKAT science, but I'll tell you guys a little bit about MeerLicht, and you will see shortly why. But let's start with ThunderCat. ThunderCat is the hunt for dynamic and explosive radio transients with MeerKAT. They study high-energy astrophysical processes which emits radio transients in radio bursts. So amongst other sciences that they are wanting to explore, here's just a few that ThunderCat wants to explore. It's galactic jets from accreting objects. They are looking for radio counterparts to X-ray binaries, and they're also looking at supernova and gamma ray bursts. Then TRAPPIM. TRAPPIM is the transients and pulsars with MeerKAT. The TRAPPIM group has installed multiple CPU GPUs in the KAPB building, and this system can form up to 400 beams on the sky. Amongst other sciences, what they are looking at is they are looking for pulsars and transients in supernova explosions, pulsar wind nebula, and Fermi gamma ray bursts. They are searching for pulsars in globular clusters, and they're looking for pulsars outside of our galaxy, and they are looking for exotic binary pulsar systems. Breakthrough Listen uses MeerKAT in commensal mode, and they've recently installed all the Breakthrough Listen user-supplied equipment in the Karoo array processing building. Breakthrough Listen is running the largest survey in the world to look for life outside of our planet, and they also make use of the GBT in order to conduct this survey. So MeerKAT, I wanted to talk to you guys about because it's an optical telescope that was constructed by the South African Astronomy Observatory, our sister organization. It is located about 250 kilometers away from MeerKAT, and it will track whatever MeerKAT is looking at. So whenever there's a transient, and when it's nighttime, and the transient was discovered by MeerKAT, we could see what the optic equivalent of that looks like. It's a 0.6 meter telescope. Meer time. So, Meer time means I need more time. Meer time is a project, and it's the key Pulsar Timing project for MeerKAT. And these are just some exciting results from recent Meer time observation runs that happened. But Meer time has various science cases as well. It has the timing of 1,000 pulsars per observation. It's timing pulsars that's found in globular clusters. It's using pulsars in a pulsar timing array in order to try and establish what the gravitational wave background noise looks like. And gravitational waves that can be detected by pulsar timing arrays are in the order of microhertz to nanohertz. They're also timing binary pulsars, which this is an example of a binary pulsar that was timed. So on the left, you've got J1644 minus 4559. So you can see the sharp profile of the pulsar. And on the right, you've got the binary pulsar, which is J1757 minus 5322. Now, for the recent discovery that was published in the Astronomy and Astrophysics manuscript of July this year, Sarah et al. Found neutral hydrogen gas within and around Fornax A, whilst working on their large-scale survey project titled a MeerKAT survey, H1 survey for Fornax. So they found neutral hydrogen gas, which are these green blobs on this picture, and these arcs are just shown to aid the eye so that you can see the hydrogen tails. This image is an optic overlay, so the green blobs is the radio image, and the image in the back is the optic image that was created by the Fornax Deep Survey using the Omega Cam on VST. So VST is the VLT Survey Telescope at Paranal Observatory in Chile. The paper is titled Neutral Hydrogen Gas Within and Around NGC 1316. And I have that paper if you guys want to read it, if anybody is interested. And lastly, here's an image of the center of our galaxy, the Milky Way, that was revealed at the inauguration in 2018. This image is a 2x1 degree portion of our sky, and it corresponds to an area of approximately 1,000 by 500 light years. The image shows star-forming regions, remnants of supernova explosions, and radio filaments. This white part over here is the galactic center. This image was created by data taken from MeerKAT as well as the GBT, and they were combined in a process called feathering. The red parts is the lower, is the not, you can't say not so bright, but like it's the yellow ones are brighter, and then the white parts is the absolute brightest objects in this image. And I would just like to take this opportunity to also thank Dr. Armentrout and Dr. Butterfield for organizing this colloquium, and Thomas Chamberlain for hosting me, and everybody else who made this trip possible. Thank you very much. Questions for our speaker?
Vereese, could you talk a little bit about what your role is in all of this?
Sure. Just let me grab some water. So I'll use the slides to do that. Okay, well, I've worked on the digitizer master controller, which is the software that communicates and controls the digitizer units. So back when I started at MeerKAT, that was like one of the first things that I got to work on. And that entailed writing sensors to monitor, for example, the temperature, as well as the speed protocol that I mentioned to you guys about. The digitizer sends speed packets over the optic fiber, so I wrote some of the speed code that is implemented for the digitizer master controller. At the moment, I am working on the TMC, which is the timing master controller. I'm working on software that combines the different hardware to produce KTT to UTC offset. Like currently we are tracking to GNSS, but the goal for MeerKAT is to be able to track the timestamps to UTC. And that's the software that I'm currently working on. Yes.
So your multicast switch, I think you said, is somewhere around 2.1 terabytes of data that it's processing before it multicasts?
The multicast switches, there are 54 of them, and they just kind of route the data. So they don't do any of the processing.
Right.
Yeah, so the 2.2 terabytes that's coming from the telescope is not actually all on one link. That's just the total of all the different ones. Yeah.
So those multicast switches, did
Yes.
you commercially buy them, or?
Yes, they're Mellanox switches.
Oh. Thank you.
Paul, you had a question?
Yeah, the beamformer correlator, you mentioned FPGAs, is that, are you also using any CPU or GPUs?
So the MeerKAT correlator beamformer doesn't specifically make use of CPU, GPUs. That is all SKARAB based, which is FPGA based. And it internally has a microblaze CPU for control, so which is called like a soft core. Does that answer?
Yeah.
Cool. Yes.
Hi, my name is Ed McCauley. I was one of the original folks at Xilinx.
Oh,
So
cool.
I appreciate you using one of the Xilinx parts. My hobby interest through SAR is Earth rotation aperture synthesis.
Okay.
So I'm curious about a couple points of your earlier block diagram. It looked like you could do correlation in both the time and frequency domains. Is that correct?
We don't do any correlation in the time domain as far as I understand. So as far as I understand that the correlator subscribes to the F-engine data, so that's in the frequency domain. But in theory, that is true, and we have user-supplied equipment that do subscribe to the timing data, and then on CPU, GPU do their own analysis.
Since you're part of the timing creation or orchestration, with what resolution are you injecting your timestamps? Not, how many nanoseconds, femtoseconds, how accurate are your timestamps?
The specification is, I think, to have been, so the uncertainty with which KTT to UTC is 5 nanosecond, but that is not implemented yet, because I'm still working on it.
Is that a little bit of
and
information?
it's still in progress. Yeah, but I think at the moment it's to within 100 nanoseconds.
Oh.
Yeah. but it needs to be better.
Well, what is the resolution of the timestamps relative to your local standard?
Oh, I don't know if I understand the question, sorry.
Irrespective of how close the local standard is to the rest of the world. When you
Yes.
timestamp, when you've got a digital stream coming out,
Yes.
how precisely can you say it was sampled?
Yeah, so it's supposed to be within 100 nanoseconds of 5 nanoseconds of UTC. The uncertainty on that.
That sounds awfully gross.
For the correlated
Well,
I think we're talking
circulars.
about the skew between the various sampling points, not between absolute time, but between all the different radio telescopes. You have to have some time accuracy between them. And it doesn't, you don't care where they are relative to UTC within
Yeah.
reason, but within each other, they need to be very, very close. What is that number? I think is what they want to know.
Oh, okay. I think if I understand the question correct now, that's what the CATS system is supposed to be doing. So it measures the round trip delay, and then I don't know the number, like I don't have a number for you, but
Well, let me put it a different way.
yeah.
When you generate a packet of sample data,
Mhm.
you've got some metadata that says it occurred at such and such a
Yes.
time. What is the least significant bit of that metadata in time?
I don't know. Like it's like a 64-bit timestamp.
You
Does
know,
that help?
but what is the rate of that timestamp?
Oh, the rate of the data going through.
Uh,
Maybe we can take it offline and draw some
Sure.
pictures and stuff.
Sure.
Yeah, sorry. And maybe you can sit in because I don't understand.
Thanks, Grace.
And maybe I don't know the answer. That one.
I'm just curious about any other science results that you may have heard about with regards to like the FRP survey, Pulsar survey. Is there anything about the status of that? you can say?
So MeerTime is up and running. So when I was at the ICTA, there was about 13 successful MeerTime runs that has occurred. By now it's probably like 15 or something more. So that's the ongoing process, and I can show you the images again. And, yeah, but like I don't know if there's any new papers that has been published.
Yeah.
Yeah.
You said that there were something like 25 proposals in. What does the proposal process look like for MeerKAT?
I
Do
don't
you
know.
Okay. can look it up.
So those 25 proposals that I mentioned, they were the open time proposals. For the large survey proposals, there were more. I don't know how many there were. Yeah, sorry. I can put you in touch with somebody that would know how the proposal works. Any other questions?
So as you're very well aware, in Green Bank we have a beamforming receiver that is also sending raw digitized data over fiber, and we've had some issues with that process. Do you guys, is it a similar process for MeerKAT, or is the digitization, are you having to recover, the byte lock and things like
No,
that?
so it's a different
fundamentally
process,
different?
yeah. We packetize the data at the digitizer.
Okay, so it's actually packets over the fiber.
Yeah,
Ah,
yeah, so
okay.
it's I don't think I ever said this, but yeah, it's an IF signal that goes over the fiber. Yeah.
But those packets have a header
Yes,
that has all sorts of interesting information.
yes. So it's
And
it'll
that's
be
what I'm trying to nail you on, but I'll do that later.
yeah, we can, I would love to chat to you more about it, because I could, and if I don't know the answer, I can definitely point you to somebody who would have the answer. Yeah. Yes.
Could you comment briefly, I know we're running out of time here, but on your breakthrough listen, could you comment on the general strategy of that portion of the project?
So the way that I understand that breakthrough lesson works with MeerKAT is that it plugs into this switch. I think this would be a better picture to have up here. So basically, this use equipment, the user supplied equipment, that is basically one of those machines would be breakthrough lesson. Well, not one, they've got multiple CPU, GPU processors, but it plugs into the 40 gig switch and then it can subscribe to any of the data products. And I think that they observe while other observations are also taking place. So they benefit from other science. So they can use that, they can also subscribe to the data and then the data gets routed to their machines, even though it's not their dedicated session. Does that answer your question?
Yeah, that's good enough, thank you.
Okay. Dave McMahon is around.
He's right there.
You should speak to him. He will be able to tell you much more than I can.
I am interested in hearing about your quiet zone.
So the quiet zone has a radius of 70 kilometers from the core. It's about 15,000 square kilometers. We also make use of the different tiers. You know, like once you get into this zone, there's no more reception. Once you get into this zone, you should switch off your phones. So it's very similar to what the GBT and GBO makes use of. But other than that, I can't tell you much more. But I can definitely put you in touch with people. Yeah. Like we had this brochure that explained about the law that was enacted. I'll try and find that and then send it to you.
So it's a federal law?
Yeah.
So how many people got caught?
In the radio quiet zone, there's like nobody. Like it's a very quiet. Yeah, there's not a lot of people
So
there.
it's quiet because nobody wants to live there?
Yeah, it can be a very harsh environment. Like in the winter it gets really, really cold, and then in the summer it gets really, really hot. Yeah.
So you're not dealing with civilians complaining?
Oh, they always complain. I think some people think that it's our fault that they don't get Wi-Fi in their town, but like they wouldn't have had it in either way, because it's not like we took anything away.
Yeah.
Yeah.
Bob and I were wondering what the most dangerous animal.
MeerKAT. Yeah, snakes. Actually, Lou said snakes. We get like other. There was a puff adder in one of the. I don't know how it got in there, but like in one of the antenna pedestals, like in one of the meetings that we had. Where's a picture of it? Yeah, so when like somebody opened up, like there's a door at the pedestal, and when somebody had opened it up, there was like a puff adder there.
That is so scary.
Yeah.
So who eats MeerKATs?
All right, any final questions for our speakers? You mentioned that there's a control room in Cape Town, and I wondered how the data gets there.
So there's a fiber links from
the
site. Well, there's breakpoints at different places. But yeah, it's over like a high-speed fiber.
So
and all the data goes to Cape Town.
Is it fiber that was already there, or did the observatory have to lay it?
I think the observatory had to lay it, but I would need to fact check that. Well, definitely like on site, like the fiber had to be laid, but like the link from Carnarvon to Cape Town, I'm pretty sure had to be laid. But yeah, I can't say that with certainty.
If you're done with the technical discussion, can you go back to your Google Maps slide? I'm curious as to what those big brown things were on.
Yeah.
Those things, what is that?
These things?
Yeah.
Those are mountains. I actually like climbed this mountain and ran all the way over here. This is about like 10 kilometers. So yeah, so you go up this mountain and then you can run all the way across and then along to antenna number 63, and then there's a road that goes over there. And then these are also mountains. So they're all really flat. So in this picture, you can actually see a bit better what they look like from the front. So that was a top view, and this is like a view. Yeah, side view.
So what cut the tops off?
The Lorax.
Are they volcanic? Are they volcanic formations with a crater?
I don't know how the Karoo Plateau originated. There are some volcanic rocks now that you mention it that some people have like explored, but I don't know the complete formation of it.
All right, any last questions for our speaker? All right, let's take